Composition and resolution of forces. An object can be pulled by two people like this, or it can be pulled by just one person. In terms of the effect of the forces, these two forces F1 and F2 have the same effect as this force F. We say that force F is the resultant force of F1 and F2, and F1 and F2 are the component forces of F. The process of finding the resultant of several forces is called composition of forces, and the process of finding the components of a single force is called resolution of forces. When we combine components into a resultant force, we only look at the effect of the resultant. When we resolve a resultant into components, we only look at the effects of the components. Composition of forces is very simple. Force is a vector, and vector addition follows the parallelogram rule, or the triangle rule. Let's take the composition of these two forces as an example. For the parallelogram rule, use the two components as adjacent sides to form a parallelogram. The diagonal of the parallelogram represents the resultant force. Now let's look at the triangle rule. Vectors can be translated. By placing the two components tip to tail, the resultant force points from the start of the first force to the end of the second. The principle of the triangle rule is the same as the parallelogram rule. The triangle is essentially drawing half of the parallelogram. If the magnitudes of two components are known, based on triangle properties, where the sum of two sides is greater than the third and the difference is less, the resultant's magnitude is less than or equal to the sum of the components and greater than or equal to their difference. Let the angle between the two components be theta. When theta is between 0 and 180 degrees, as theta increases, the resultant magnitude decreases. When the angle is 0, meaning the components are in the same direction, the resultant is at its maximum, equal to the sum of their magnitudes. When the angle is 180 degrees, meaning the components are in opposite directions, the resultant is at its minimum, equal to the difference between their magnitudes. Resolution of forces is slightly more complex. We can view it as the inverse process of the composition of forces. According to the parallelogram rule, composition finds the diagonal from the adjacent sides, so resolution finds the adjacent sides from the diagonal of the parallelogram. But we quickly realize that a single diagonal can correspond to infinite parallelograms. This means a force can be resolved in infinite ways. So, which one should we choose? There is a special type of resolution where a force is resolved into two mutually perpendicular directions. We call this method orthogonal resolution. In high school physics, orthogonal resolution is used in over 90% of cases when resolving forces. The advantage of orthogonal resolution is that it creates a right-angled triangle, allowing us to easily solve for the forces using simple trigonometric functions. Let's briefly discuss trigonometry. In this right triangle with sides A, B, and C, let this angle be theta. The ratio of the opposite side, A to the hypotenuse C, is the sine of theta, written as sin theta. The ratio of the adjacent side B to the hypotenuse C is the cosine, written as cos theta. And the ratio of the opposite side A to the adjacent side B is the tangent, written as tan theta. Here are trig values for common angles. The 37 and 53 degree angles are particularly special because their sine, cosine, and tangent values are all rational numbers, making them very easy to calculate. Now back to resolution of forces. If we know force F is 10 newtons and the angle is 45 degrees, we can use trigonometric functions to easily find the magnitudes of components F1 and F2. Now we know about orthogonal decomposition, but you must have noticed that even with this method, there are countless ways to decompose. So, which one should we choose? This depends on the specific situation. For example, an object moves to the right at a constant velocity. Given its mass is m and the angle between force F and the horizontal is theta, find the coefficient of kinetic friction. Since the object moves at a constant velocity, the forces are balanced. Analyzing the forces, gravity, normal force, and friction, we decompose force F into horizontal and vertical components. Using the kinetic friction formula and horizontal force balance, we find the friction magnitude. From the vertical balance, we get the normal force. Substitute these to find the coefficient of kinetic friction. Let's look at another example. An object is at rest on an incline. Given its mass is 1 kilogram and the incline angle is 30 degrees, find the friction force acting on it. Since the object is stationary, the friction is static friction. Analyzing the forces, gravity, normal force, and friction. Now, we decompose the object's gravity into components parallel and perpendicular to the incline. It's easy to see this angle is theta. Based on the force balance along the incline, friction F equals mg sine theta. Substituting the values, we find the friction force is 5 newtons. Have you mastered these simple concepts?